Hello everyone, and welcome back. Today we're going to continue our exploration of linear algebra and introduce two very useful tools that can actually make analyzing matrices and their interactions with one another quite easy. We won't get into the applications in this video, so we're just going to focus on the mechanical components for these two tools. The first tool that I want to introduce is known as the vectorization of a matrix. So let's first off define what it means to vectorize a matrix. So let's assume that A is an m by n matrix, so rectangular, square, any is okay. So let that be a matrix. Then the vectorization of a matrix will send an m by n matrix to another matrix U whose dimensions is m times n by 1. So we'll send a matrix into a column vector. All right, so let's look at the general form of what that looks like. So that means if we take our arbitrary matrix, A11, A12, down to A1n, A21, A22, down to A2m, all the way down to AM1, AM2, and AMN, which is obviously an m by n matrix, then this is going to turn it into a column vector of the form A11, A21, all the way down to AM1. So that's the first column, and we're going to be transposing this vector, by the way. And then A12, A22, all the way down to AM2. So that's going to be the second column, all the way down to the last column. So A1n, A2n, all the way down to AMN, transpose of that. Right? So this looks like a column. So let's look at a couple numerical examples just to make sure we understand this structure. So first easy example, suppose we want to vectorize 3, 5, 7, 6. So our first column is going to be 3, 7, our second column is going to be 5, 6, and that's going to be stacked underneath one another. So this 2 by 2 matrix is mapped to this 4 by 1. Another example, let's assume that we want to vectorize a row vector, let's say 7, 6, 8, and 2. So that's obviously going to be a 1 by 4 matrix, which is going to be mapped to a 4 by 1 vector, which is going to be 7 in the first column, 6 in the second column, 8 in the third column, and 2 in the fourth column stacked on top of each other. Another example, suppose we want to vectorize a column vector, 1, 3, and 5. So if we only have one column, then that's just going to be itself, so 1, 3, and 5. And let's just take another matrix just for exercise. So 1, 2, 3, 4, 5, and 6. So that's going to be equal to 1, 4, 2, 5, 3, 6. So that 2 by 3 matrix is going to be mapped to a 6 by 1. Now it's very important that you keep track of what we're going with here, because if we vectorize, say 1, 4, 2, and 5, 3, 6, this is also going to be equal to the vector 1, 4, 2, 5, 3, and 6, right? Which is the same 6 by 1 matrix as mentioned here, right? So this mapping from matrices to vectors is not one-to-one because we have obviously two different matrices that map to the same element in the range of this particular mapping, right? So if somebody were to give you that particular size and say, okay, what is the inverse mapping of this vector? They would have to tell you the size that the original matrix was. For example, if they say it was a 2 by 3, then how would you sort of do that? So if it's a 2 by 3, that means we have 3 columns in this particular vector. In particular, we would have to partition it into 3 pieces. But obviously, if we originally started with a 3 by 2, that means we would have to partition this into 2 equally sized matrices, 1, 4, 2, and 5, 3, 6, and those would be the columns of the original matrix. Now, let's talk about a couple theorems. I'll do an example of each, and I'll leave the proof for you. So the first theorem that I want to introduce is the vectorization of the sum of two matrices. And obviously, A and B obviously should be the same exact size for this to make sense. One can show that this is equal to the vectorization of A plus the vectorization of B. Keep in mind that's a column and that's a column, so this, of course, is going to be a column. Okay, so let's just illustrate this with a nice example. Suppose we have A is equal to 1, 2, minus 1, 5, 2, and 1. Let's assume we have B, which is equal to 5, 2, 1, and 1, 2, and 3. Because if you can usually work through a good example, usually constructing a general proof for the arbitrarily case, it usually is not that hard. So if we do A plus B, that's going to be equal to 6, 4, 0, 6, 4, and 4. And if we vectorize A plus B, that's going to be equal to 6, 6, 4, 4, 0, 4. Its transpose, right? So that's going to be our first line, and now let's test the other side. So the other side is going to be what? So the vectorization of A is going to be equal to 1, 5, 2, 2, minus 1, 1, transpose. The vectorization of B is going to be equal to 5, 1, 2, 2, 1, 3, transpose. And then from these, the vectorization of A plus the vectorization of B is going to be equal to, and when we write it as a row vector or the transpose of a column vector, it's actually very easy to see what's going on here, I think. So that's going to be equal to 6, 6, 4, 4, 0, and 4, transpose. And obviously these two lines are equal. So it's true for this example, and that should give you a guide for a proof for the general example. Another theorem that is actually quite useful is the following. The vectorization of a constant times a matrix is going to be equal to the scalar product of k times the vectorization of that particular matrix. And here k is a scalar and A is a matrix. So let's just illustrate this with an example. So example, let's assume that we have A, 1, 2, minus 1, 5, 2, and 1. And let's multiply this matrix by 3. So that's going to be equal to 3 times 5 is 15. 3 times 2 is 6. 6 minus 3 and 3. And let's vectorize 3a. So that's going to be equal to 3, 15, 6, 6 minus 3 and 3. And now what we want to do is we want to vectorize a, because this is the first thing we need to compare to. So the vectorization of A is going to be equal to 1, 5, 2, 2, minus 1, and 1. And if we multiply this vector by 3, we're going to have 3, 15, 6, 6, minus 3, and 3. Right? And if you compare these two vectors, you can clearly see that those are indeed equal to each other. So therefore, if you should be able to show it for two reasonably different matrices in an arbitrarily scalar, like don't choose 1 or 0 because those will give you special cases. Choose like some weird number like 3/5 or 7 or -3 or something. And that should give you a sketch for the general proof, right? So if we combine these two theorems together, what do we have? So that means the vectorization of C1a plus C2b is going to be equal to what? Well, that's obviously a matrix, and that's obviously a matrix, so that's going to be equal to the vectorization of C1a plus the vectorization of C2b. And these are constants, so they can, in some sense, factor out. So we have, for example, C1 times the vectorization of A plus C2 times the vectorization of B. And what do we have? Well, if that is equal to that, that means this operator is a linear operator. And that obviously has quite a few important applications, at least in theoretical vectorization. So the next tool that I want to introduce that is sort of independent from vectorizations of matrices is the Kronecker product of matrices. So we begin by defining two matrices A and B. They can be the same dimension, but they don't have to be. So they can have different number of rows, different number of columns, or different dimensions overall. And you can define the Kronecker product between these two matrices, in particular A with B, which is going to imply that possibly this product is not going to be commutative. And we're going to be denoting it by a circle with an x in the middle, subscript k. So that's going to be the Kronecker product of A with B. And it's going to be a matrix. So let's just actually walk through this definition just to make sure we understand it. So the Kronecker product of A with B is going to be equal to, so let's first off start listing the elements of A. So we have A11, A12, all the way down to A1M, and then we're going to have A21, A22, all the way down to A2M, and that's going to continue all the way down to AM1, AM2, all the way down to, no double subscripts of course, so AM2, all the way down to AMN. And what the Kronecker product does is it multiplies each of these scalars by your matrix B. So B there, 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 and B there. So this is the Kronecker product of A with matrix B. Now if you sort of take a look at what's going on here, what do we have? So in each of these rows we have a matrix, and in each of these columns we also have a matrix. So how many rows does B have? Well, B has k rows, so there's going to be k rows here. There's going to be k rows here, all the way down to k rows here. But keep in mind we have n rows of constants, so that means we're going to have n k rows total in this particular m k rows. Let's not get our letters mixed up. So m k rows, because that's an m. And how many columns do we have? Well, B has L columns, so there's going to be L columns there. We have L columns there. We have L columns there. And we have a total of n columns of constants. So that means we're going to have L times n columns total. That means the Kronecker product between A with B is going to have mk rows by ln or nl columns, right? So it's a what some people call a block matrix, right? Because this is a matrix, this is a matrix, this is a matrix, and so on for each of these blocked off cells. So let's work through a couple examples to see if we understand this definition. So example 1. Let's define A to be the matrix 1, 5, 2, minus 3, 2, 7. Let's define B to be the matrix 8, 2, minus 3, 5. So A is a 2 by 3, B is a 2 by 2. So what are going to be the dimensions of the Kronecker product of A with B? So we're going to have 2 times 2 rows, and we're going to have 3 times 2 columns. So we're going to be looking for a 4 by 6 matrix when we're done with this calculation. So the Kronecker product of A with B is going to be equal to, so what I want to do is just first off list my constants. So I'm going to have 1, 5, 2, minus 3, 2, 7. And then I'm going to throw my 8, 2, minus 3, 5. 8, 2, minus 3, 5. Need a little bit more room there. 8, 2, minus 3, 5 in each of these cells. 8, 2, minus 3, 5. So once I have that, then I can perform the scalar multiplication of those constants with each of those 2 by 2 matrices. So what is that going to give me? So 1 times the matrix is itself, so we're going to have 8, 2, minus 3, 5. Minus 3 times that matrix is going to give us minus 24, minus 6, positive 9, and minus 15. And then in the next cell, we're going to have 5 times 8, that's going to be 40, 10, minus 15, 25. and then 16 for minus 6 and 10, 16 for minus 6 and 10, and 56, 14, minus 21 and 35. Right? So this is our 4 by 6 matrix that represents the Kronecker product of A with B. Right? So let's go through some theoretical properties associated to Kronecker products that are actually quite useful to know. And I'm not going to prove these, as, at least for now, and I'll leave some of these for your curiosity to solve. So the first one is actually pretty easy to solve, at least proof-wise. So if we have a scalar times a matrix and the Kronecker product of that with matrix B, one can show that this is actually equal to A Kronecker product with a scalar times B, and this is actually equal to the scalar multiplied by the matrix A Kronecker product with B. Here, K is a scalar, and A and B are matrices. So that's actually pretty easy to solve, so I invite you to try that out. The next is that the Kronecker product of A with the sum of two matrices B and C, so B and C need to be the same exact size, of course. That's going to be equal to the Kronecker product of A with B plus A Kronecker product of A with C. Right? And it's also going to be true in the other direction. So one can show that A plus B Kronecker product with C is going to be equal to A Kronecker product with C plus B Kronecker product with C. So it's left and right distributive, which is actually pretty nice. So if we combine these two theorems together, we can actually get another fascinating conclusion. So if we do A Kronecker product with C1b plus, let's call it B1, and C2 B2, what are we going to get? So obviously C1b1 and C2b2 are just matrices, so we can distribute this Kronecker product over that sum. So this is going to be equal to A Kronecker product with C1b1, and then plus A Kronecker product with C2b2. And we know that constants can sort of factor outside of the Kronecker product. So this is going to be equal to C1 times the Kronecker product of A with B1, and then plus C2 times A, the Kronecker product with B2, right? So there's the input, and that's the linear combination of the output. So we can say that A Kronecker product with something is also a linear operator, right? Which of course depends on that first matrix A. Now, there are some other properties that you probably should be aware of, and they're very interesting to prove. Not necessarily the easiest, but once you become a little bit more comfortable with Kronecker products, they're actually not too bad. So let me just list them out here, just for your reference. So the first of these is what is called the mixed product property of Kronecker products. So A Kronecker product with B times C Kronecker product with D. And obviously these matrices need to be dimension appropriate. So A Kronecker B and C Kronecker D have to have the same inner dimensions, but A, B, and CD can practically have whatever dimension they want, as long as those inner products agree. This is actually equal to the product of matrices A and C, Kronecker product with B and D, which is actually pretty interesting. So the Kronecker product and matrix multiplication sort of interchange with one another, which I find pretty interesting. Another property, which actually is tied to this one, is that the Kronecker product of A with B Kronecker C is equal to A Kronecker B Kronecker C. So what property is this? Well, that's obviously the associative property for Kronecker products. Now, when it comes to inverses as transpositions, we would usually like nice properties with that. So for example, if we have the Kronecker product of A and B, and we want to find the inverse of that, then this actually comes out to the inverse of A, Kronecker product with the inverse of B, provided that A and B are, of course, square invertible matrices. And if we have A Kronecker B, so A Kronecker B, and we take the transposition of that, that actually gives you a transpose Kronecker B transpose. Now, if you remember just basic matrix multiplication, if we have A, B inverse, this is going to be equal to B inverse A inverse, and A, B transpose is going to be equal to B transpose A transpose. And it's only equal to A inverse B inverse and A transpose B transpose if and only if A and B commute, which they don't necessarily have to. But here, A and B, again, don't necessarily commute, but inverses and transpositions distribute nicely and preserve order when it comes to Kronecker products, right? But keep in mind, note that A Kronecker B is not necessarily equal to B Kronecker A. Now they will have the same dimensions, but they will not be the same elements necessarily. And one last property that I want to mention in terms of determinants is that the determinants of the matrix A, let's assume that A is an m by m matrix and B is an n by n matrix. So the resulting matrix will be an mn by mn matrix, which is square, so the determinant is well defined. This can actually be found by the determinant of the square matrix A raised to the power of n times the determinant of B raised to the power of m. Notice that m by m is the size of A, and m is associated to the power of B, and n by n is the dimensions of B, and that's raised onto the power of A. Right? And those are some properties of Kronecker products that you definitely should be aware of when playing with Kronecker products, and the proof of them, of course, is adventurous, as always. Now, with those two things, those independent entities, vectorization and Kronecker products, you may think, okay, well, do they share an interesting connection? There's one theorem that actually brings these two things together, which actually opens many doors for applications. So let's get into that theorem and what it says. Before stating directly the next theorem, I want to introduce three arbitrary matrices, at least to some degree: A, B, and C. A 1 by 3, B a 3 by 3, and C a 3 by 2. Now there is one requirement that I need for this example to work. In particular, A, B, C, the product of these matrices with standard matrix multiplication must be defined. So obviously 1 by 3 times a 3 by 3 will be a 1 by 3, and that resulting matrix must also match as well, and that's going to result in a 1 by 2 matrix in the end, right? So this matrix is defined under normal multiplication, and you should be able to find that ABC, being this lonely little 1 by 2 matrix, is going to be the matrix 120, 305. Right? So let's just keep that in the back of our mind, and you can try that if you want to practice your matrix multiplication. Right? Now, let's get into the vectorization and Kronecker product relation that I want to introduce. So the first thing that I want to look at is the vectorization of that 3 by 3 matrix B. So that's going to be equal to 1, 3, 5, 2, 4, 6, 5, 2, 1, the transpose. Right? So this can be the vectorization of that particular matrix, which obviously is a 9 by 1. The next thing that I want to look at is the Kronecker product of C transpose with matrix A. And this order, you may think, oh, well, that's a quite strange thing to do, but you'll see the magic of it soon. So this is going to be equal to, so the transpose of C is going to be equal to 1, 7, 1, 5, 2, minus 3. Then we're going to be taking the Kronecker product of that with matrix A. So 3, 5, 2. Right? So what is that? So this is going to be a 2 by 3 matrix. That is a 1 by 3 matrix. So this resulting matrix is going to be a 2 by 9 matrix. So 2 rows, 9 columns. And I invite you to do that calculation on your own. But this is going to be equal to, I can list it out for you once you actually work it out. So we're going to distribute 3, 5, 2 to each of those 6 elements. So we're going to have 3, 5, 2, 3, 5, 2, because we have 1 and 1 there. And then we're going to multiply that by 2. And then we're going to have, let's see what that comes out to. So 3, 5, 2 is going to be equal to 6, 10, and 4. And then 3, 5, 2 times 7, that's going to be equal to 21, 35, 14. 3, 5, 2 times 5 is going to be equal to 15, 25, and 10, because 2 times 5 is 10. And then 3, 5, 2 times minus 3, so that's going to be equal to minus 9, minus 15, and minus 6. So that's going to be our 2 by 9 matrix. So the next thing that I want to do is take this C transpose Kronecker product with A and multiply that by vectorization of B. Because notice this is a 2 by 9 matrix, this is a 9 by 1 matrix, so therefore a 2 by 9 multiplied by a 9 by 1 will be equal to be a 2 by 1 matrix. Does this number look familiar? It should. So if we do that, so C transpose Kronecker product with A, this is a quite tedious but not hard calculation. That's going to come out to some matrix. Take a guess of what it is. So it will come out to 12305, which is a 2 by 1. So do those things look the same? Well, it should. So if we look at the vectorization of ABC, which is the vectorization of the matrix 120, 305, that's going to be equal to 120, 305, which is also a 2 by 1 matrix, and that's actually the same matrix as here, which is pretty neat, right? So obviously these matrices aren't exactly the nicest of matrices, but it begs the question, are they equal by chance? And actually no. So one can prove, in this theorem, I don't know, depends who you talk to. It's actually quite fun to prove, but not exactly the easiest. But the vectorization of the product of A, B, and C is going to be equal to the Kronecker product of C transpose with A times the vectorization of B. And this actually serves quite a few applications, which I won't get into here. So there's 2 new tools to add to your tool belt, vectorization and Kronecker products, that have a variety of examples which we won't get into here. So I hope you enjoyed this video, and I'll see you in the next one. Take care.